got 6 and 11 control devices. Is that right?
Yeah.
What's the chapter number? How do you know, Bernard? You already got the book memorized?
I was looking at my book
Okay.
last night while I was at work.
Control devices. What chapter is control devices? Bernard, y'all can look at the index in the front, right? Not the table of content in the front, right? Yeah. Chapter 6. What is it in your book, Gilbert?
Mechanical input control device.
Chapter 6? Okay. Wow.
Page 140.
So we'll look in this chapter, we'll look at each button, selector switches, joystick switches, limit switches, daylight night switches, pressure switches, temperature switches, flow switches, smoke and gas switches, level switches, wind metering. And somebody's probably have to go out to my HHR and bring my big bag in. I can bring it up. It's too heavy for me to get up there with my backpack. So I can show y'all some of this stuff. Somebody do that for me?
That's the basic.
Yeah, any control system. So we have inputs into the control system, then we have the control that makes the decision. And then sooner or later we're going to output. Yeah, somewhere. So a computer is a control system. So you got inputs, right? What's your inputs on your cell phone? What's your inputs on your cell phone? All these buttons, right? And actually, very few inputs on a cell phone because we have what we call a touch screen. We simulate a lot of stuff with our computer, but that's our input. Most of y'all have true volume controls, right, on one side, and then most of y'all have a standby and an on button on the top, and some of y'all's got a power button on it where you can actually power your phone off eventually. So those are all input devices. And then we bring that into a control section, and the control section is what's making decisions on what to do with those inputs. And eventually, what's it going to do? It's going to output. So your phone, you drop your phone, your display gets all broke up, your display don't work anymore, then you're going to throw it away because you've lost, even though the processor and everything might be what? Might be perfect, the memory might be perfect, but it's basically useless because either you lose an input or you lose what? You lose an output. Or if you lose your decision making, this will be when your cell phone just literally dies, right? You don't do anything. In the motor controls, we basically combine the control and the section we call decision making. So this is where all your input devices are. So all your input devices are making decisions, right? You understand? If this and this, or this, that's where all your logic is right there. And we needed to talk about another logic too. We'll go back and do that in a minute. I thought it was exclusive ORs and exclusive NORs in the textbook. Oh wow! Look out these those. Those are very, very, very common. I've had to use them a couple of times myself, even on PLC logic. So on a PLC, on a ladder diagram, we got decisions on the left, right? This is where all your push buttons are going to be, or all your input devices are going to be, or control devices. And then on the right, this is where our output is. Now we have very limited outputs we can put over here. We put lights over there, right? We can put relays, we can put solenoids. And some very, very small motors, because the control section is not intended to run power, is intended to make all your decisions, right? So that's your control. That whole ladder diagram that y'all wiring up, that's the whole control circuit. That makes sense? Everybody okay? So some of the control devices that we've already dealt with, of course, we've dealt with push buttons. Not selector switches yet, even though some of y'all tried to wire those up. We had to have joysticks. We do have limit switches in here. We don't have daylight switches, but I don't know why they call them daylight switches. We have light sensors, light sensing sensors in here. If you take the sensors class, we'll deal with that. Temperature sensors or switches. Now, when we say switches, these are digital. which means what? With whatever they look for, when it's true, it's going to give you, it's going to let the signal pass through, right? If it's false, it's going to block it. So these are considered to be digital devices. I don't know, in sensors class, we'll let y'all play around with some analog devices. So in sensors, we deal with pressure switches, we deal with light switches, we deal with temperature switches, we don't have flow switches. We do level switches without using these meters. Of course, we're dealing with automated systems right now. And of course, troubleshooting and smart input devices. Are we okay? So this is the makeup, and y'all have already seen these. This is the makeup of basic push button panels. We have contact blocks that normally we can put more than one back here. And, we have a set in here, but I don't know where it is. Like I said, I hadn't taught a class for a while, but this is a push button of an industrial push button. So industrial push buttons have to be better quality than a push button you would have in a car, right? You understand? Because these are in very, very harsh environments. So basically, we have a push button, and then we have some type of plateau or mounting, and the function of this guy is to prevent you from accidentally hitting the push button, right? And we have different mounts. Sometimes it's got a groove cut in it, so you can push it like this with a glove instead of having to push it like this. So this, you literally got to come in and do push it head on, right? You can't push it from the side. So that's the purpose of this. Then normally under this, we'll have what they call a legend plate. And what's a legend plate? It tells you what the push button does. Now, so we have legend plates on our push button stations that says what? Start, stop, forward, reverse. But that's the legend plate. It don't mean in our class that's what you got to use it for. They just want to give you an example of what it would look like in the industry with those legend plates on there. Basically, right now we're looking for normally open push buttons, normally closed push buttons, or the one that we're using most often is the double post single throw, right? So we got right? So, and then on the back of this, on industrial contacts, we have, these are the actual contacts back here. And this is where we would connect the wires. So, and what's nice about these is, you can see these two big, screws right here, is we can do what? If we got a problem with them, instead of replacing the operator and everything, we can do what? We can just replace the contact block. And then we can keep stacking these things up. You'll see these little alignment keys right here. And we can keep stacking these things up. So one operator might be operating what? 15 different contacts or more than that. Right? That makes sense? And so this gives us a normally closed contact. So the normally closed contact is on this side. And then a normally open contact's on that one. Now what this does, it actually puts the symbol on there for you, right? So there's the symbol for the contact, and this shows this is normally closed. So if I was to take an ohm meter and put it across here, right now the ohm meter would measure infinity or overload, and then when you push it, it should go to 0, right? You understand? That's the normally open one. The normally closed one, when I measure it right now, it should measure pretty close to 0 ohms, and then when I push the normally open, the normally closed, it should open, right? Everybody okay with that? Here you go, Rizal. So this is a pretty standard industry contact of the makeup. And a lot of stuff in industry is not going to be like the push buttons in your car where if one goes bad, you just can't fix them because they're all sealed up. So normally if you got a button in your car that goes out, you got to just replace it. Just about all your industrial push buttons are going to be repairable. So if the contact comes out, if you mess up a contact, you can take it off and you just put another one on there, right? So you can carry spares, especially if you use the same push buttons all over your plant. Then you don't have to carry 1,000. You don't have to carry spares for each one, right? So this is a selector switch. Everybody okay with these? So these are about the only switches you'll see in industry. They got nice big knobs on them, okay? So our selector switch is on our light panel. On the light panel. So this is not quite the one that you've got. So these are our newer ones that we're using for our sensor trainer. But it's going to be mounted on the same panel. Okay. So this is a selector switch. So it's got a nice big operator on it, right? You'll see that. So you can grab it with a glove hand, right? And then this one, this is the legend plate. So we still have a legend plate on there, and this says hand and auto. In our class, that really don't mean anything, right? You understand? They're just giving us an example of what these things would look like. And this is a three position selector switch. So we got a set of contacts that's over here. So I just made a set of contacts. Here, both set of contacts would be open, right? You understand? This one would close, and this one would open. Everybody understand that? I think the two position or three position is on the next slide. Now, the way we would draw these symbols, for this, sorry. I must be looking at the wrong thing. No, that's the only thing I did. So this is a push button on the side, right? These are selector switches. These are push buttons. These would be what we call a single pole double throw, right? Everybody okay? This would be normally open. This would be normally closed. These I got them drawn real close together. This would be a what? Single pole double throw, right? Everybody okay?
Is that a double pole?
This is a double pole double throw right here. Now we can simulate a single pole double throw by connecting two sides together. So we'll do that a lot. And that way we'll get a normally closed contact and a normally open contact. So you won't see many single pole double throws. You'll see a lot of these because what's nice about these, if you use the top two, then you got a normally closed push button. If you use the bottom two, you got a normally open push button, right? You understand that? And then of course, so that's what we have on our push button panel. Are we okay? Yeah, nay? Push button stations, enclosures that protect the push button contact block and wire from the dust. So that's what we're saying. Normally these guys are sealed up. They're nice and sealed right, you understand, because in the industry, there's a lot of dust and crap that floats around in the air that you wouldn't necessarily, out at U.S. Steel, it was awful. We had a lot of graphite dust. It was a powder. It was all over the place that you get from making steel. And it's a really good conductor, so you have to be really careful where that stuff got at. And, yeah. And, so it was all over there. If they would have took me a picture of me then, I'd probably be in trouble like the governor of Virginia. We were replacing some big monitors. They had closed circuit TVs in a power station, and I reached up there and grabbed that stuff, and that thing must have had 2 inches of graphite on it. And when I pulled it down, what happened? Right in my face. I mean, right in my face. So that was a mess. But it was all over the place, and it would puff when you walked. It was a mess. Anybody that worked out at U.S. Steel just got into that. So how we mount them, how the contacts are mounted. Normally when you buy these things, they'll come with a what? A sheet. NEMA, what does NEMA stand for? Electrical Manufacturing. And then IE, International Electrical, I think it's Commission. Yeah, thank you. I keep wanting to say, So what we do on a selector switch is this is a two position selector switch. One could be forward, one could be reverse, one side could be open, one side could be left, one side could be right, or just ours is labeled auto and manual. But what it shows us is it gives us a solid line going to the left, and then it gives a dash line going to the right. Does that make sense? So what it's telling us, if we put it on the right side, then we're going to close the top set of contacts, and the bottom set of contacts are going to do what? They'll open. And if I move it to the auto side, then what's going to happen? Then the top set of contacts are going to open, and the bottom set of contacts are going to close. Everybody okay? And what's this a symbol for? Not a hook switch, right? Yeah. And of course, that's just a manual single pole, single throw switch.
So let the switch have two different wires.
Well, actually, we'd have four. This one would have four. We could have a selector switch that's got more than two positions. I've seen them that had, four. You're flipping through, and each one of them would open a set of contacts, and that's why it would be very important to get drawing. It shows you what contacts are open. So if you've got 8 switches in there, then you're going to have 16 wires coming. 2 on the input side, 8 on the input side and 8 on the output side, right? If you use all the switches. So yeah, this guy's going to have 4 wires coming because it's got 2 divisions, right? Understand that? 2 on the input side and 2 on the output side. If you use all of it. I've never seen one. I'm not going to say that. We could only use one of the switches though, and call one of them off and call one of them on. And don't even wire on the other 2 wires. So this is what we have. We have a 3-position switch. So we have an off position. So when you put it in off position, notice it shows the dot, and it shows it would be this guy right here, right? Okay, which means what? This would be broke, and this would be broke, right? I understand that. Yes or no?
What do you mean broken?
It'll be open. It'll be open. So it would be in the center position. So if I was to come and draw the circuit and leave out the rest of them in the center, and they're going to draw all of them, guys. But if I was to come over here and leave out the center, so if I select this thing in the off position, then what happens is the operator's sitting right there, which is it's showing it. So see, it's showing the little bubbles here, and it's showing the position it would be in when you have it in the what? In the off position. Now, if I switch it to the manual position, this is the solid line. It goes to the top. So what's going to happen is it's going to close this one, but do what? Open that one. And then if I go all the way to the right, to the auto position, then it'll close the bottom one and open the top one. If I put it in the center position or the off position, then both of them are going to be open, right?
When we come across this, like, in other stuff, it'll be drawn like that, or?
Or you will have to draw it like that. If it requires you to draw it, you got to draw it like this, right? So if you take the sensor class, which is a good class, guys, it's coming up in a T2, you're going to, and this is why we require you to have motor controls. All the diagrams in there you're going to draw, except for the first couple of lines. And then after that, it's going to tell you, you're basically going to design the circuit around the sensor to do whatever it says you do. And you're going to have to use the industry standard symbols, right? And you're going to have to put these dots out here. In my class, guys, if you don't put the dots right there, what does that mean? It's not connected. Now, the big difference between a solid dot and an open dot, what's the difference between this guy and that guy? It's a terminal. It's a terminal. It's what we connect to, right? So on your input devices, these right here are going to have the open dots, not the solid dots. So in this class, all your labs are drawn. So if you use the selector switch, it's going to be drawn, right? But like I said, later on, you're going to have to draw. And also some of your chapter quizzes, it's going to require you to make some drawings. And the drawings are going to be to industry standard. There is no curved lines in any of electrical drawings. Everything's at 90 degrees. They're either straight or what? 90 degrees, right? You understand that? In fact, that's true on most trades. I know in electrical or for electricians, they do some curved lines, but they mean something. So y'all understand that, Sybil? Okay. Sometimes they give it in a truth table. We call these function tables truth tables. What truth tables does, it shows you how the thing responds for all positions that you can put the switch. So the X up there means that circuit is closed, and the O means the circuit is what? Open. So up at the top, you look, we see an A and a B. Y'all see the A and B up there in your book? So when we see the A and B, it says if I put it in the number 1 position, then A is going to be closed and B is going to be what? Open. So that means it's going to be the way it's drawn. If we put it in position 2, then A is going to be open and B is going to be closed. Did I say it right? A is going to be open and B is going to be closed. So it means that would close this circuit and do what? Open that circuit right there. So this is another method of drawing. So here they don't put all the dashed lines and the dots and stuff inside the symbol. So this makes it a little clearer for the symbol to be drawn, right? You understand? Make sense? So down here, this is a 3 position. It gives us the 3 positions. 1, 2, 3. So in position 1, the contact labeled A is going to be closed. B will be what? Open. In position 2, the contact label A is going to be open and B is going to be open. And then in the position 3, then A will be open and B will be closed. Y'all understand that? Are you okay? So notice this makes the drawing a little simpler than this guy right here. Right? You understand that? Everybody understand that truth table?
You did it wrong.
Huh?
All right, truth table and PLC.
Yeah, we talk about truth tables and PLCs. We talk about truth tables and digital. So what a truth table does is says how things responds to the combinations of the different combinations of the inputs. And it's a lot easier to follow than trying to indicate it on a drawing. Especially if we add one more position to this thing, what would we do with this guy right here? How would we indicate a 4th position? Well, it would be real hard to do, right? You understand? But it wouldn't be hard back over here because I would say circuit A, circuit B, circuit C, right? You understand? Or maybe circuit D, and then I could put a truth table over there and show y'all how this thing responds to depending on which position you have there. So we literally could come up with a switch that closes 2 circuits and opens up 1. And then in the next position it does what? Opens 1. Yeah, and so it's so the truth table to me, this works okay until you get past three positions, and after you get past 3 positions, it gets very complicated to come up with one symbol that represents all 3 of all the different positions. So odds are the switch. This is not going to be on the drawing. It's when you buy the switch, it's going to come with the what? It's going to come with the truth table. Are you okay? Any more questions? So this is a joy switch. So this is a joystick. This is a 4-position joystick. We could have up to 8 positions on this thing. You'll run into a lot of these on earth moving machines and cranes and stuff like that. You'll run into a lot of these. You got forklifts. So this is only a 4-position joystick. Most of them are. You know, if you got a game you're playing at home, a lot of times it only has what? 4 positions. Sometimes it has 6 if you hold 2 buttons at the same time. But all you're doing is switching, another signal. Yeah, what are joysticks? The way this works, we have a truth table up here. right? Y'all see that? So if I have it to the right, it's gonna make circuit A, and it's gonna open what? Or contact A, it's gonna open B, C, and D. If we have it left, it's gonna open A and close B, and open C and D. If we push it up, it's gonna open what?
A and B.
Yeah, if we push it down, they don't show us the center position. So the center position, I don't know why they didn't show that, but the center position should be what? It should be all opens, right? Yeah. So, this is the way they could draw it instead of using the truth table, is they come up here and put a dot indicating the direction this contact is closed. So notice the dot on that one. So it says that one would close if I put it to the what? Right. This one would close if I put it to the what? Left. This would close if I push it up, and this would close when I push it down. So this would indicate if I don't push it left, or if I don't push it right, if I don't push it up, then all these are going to be false, right? And whoever did this didn't put that position in the truth table. So up there they should have said center position. All of them should have been zeros, right? Now are you okay there? This makes sense. Yes? Okay. These are limit switches, and we passed around limit switches before. Everybody okay? So a limit switch, these guys have been around for years. They're still used all over the place. They're very cheap relative to other, what we do have, this is called what we call a proximity sensor, even though we don't, limit switches have been around. So when IBM decided to load the main operating system of their computer off a disk, it became known as a disk operating system. My computer loads it off of a disk, but we don't call it a DOS because the DOS was around so long. It was a text-based operating system that it got the privilege of being called a DOS. After that, we named them like Windows XP and Windows Vista and Windows 10. But all those are disk-based operating systems, right? You understand that? So this is what the limit switch is. Even though the limit switch is a proximity sensor, which means this guy is going to detect when something's at a certain spot. It don't know the position. All it knows is when it's at a position, right? Does that make sense? And these guys became known as limit switches because this is what they basically were originally used for. So it prevents on garage door openers. We have limit switches on garage door openers. So when the thing gets all the way to the top, it hits the limit switch, and what does it do? Stop. And now it won't go any higher because it's up against that limit switch, right? You understand? And then when you hit the down button, it runs until it does what? Hits the bottom limit switches. We have them on elevator doors. So how does the elevator door know when the door is open and the door is closed? It's got a what? It's got a limit switch that actually hits that switch up there to let it know. So to know it's either closed, it's up against this limit, or it's fully open, it's up against that limit, right? So we had motors that would run forward and reverse, and it would hit it when it would try to move them a certain direction. So these became known as limit switches, even though they have a lot of functions. We use these things to count things, we use them for a lot of things, but they are called limit switches. So we're going to look at some proximity sensors that are electronic. So now, even though the limit switch is a proximity sensor, it has its own name. So now in today's society, when we talk about a limit switch, we're talking about an electronic switch, a non-contact switch. So we got non-contact sensors that can sense limits. Okay. So these guys have to make physical contact with whatever they're trying to find out when it gets to a certain position. So this don't know the actual position. It only knows when it's at a position, right? Does that make sense? So we got position sensors. Like when you walk now, just about every door you walk into in a commercial place has a position sensor on it. When you come up and you get into that position, right, what does it do? It opens the door for you. you can come straight on or you can sneak in from the side. So it knows your what? It knows your position. It don't know you're at a certain spot. It knows your position as long as you're within that range. So these guys have to make physical contact. So this is a really good picture. So whatever this is in motion, you put something that the limit switch can hit up against when it gets to a certain position, to the position you want. A lot of times that is we can move it around. Okay, you know, we could take it over to the other shop. We might try to do that because I don't think we're doing a class in there on our night, and we'll look at some of these control devices besides that. So what would be the advantage of this guy? Well, they can be big, so some of them can handle a lot of current. They can be little tiny things, which we'll run into in most of our automated manufacturing, where the limit switch doesn't have to handle a load. The biggest problem we have with these things is they're what we call electromechanical devices. And what that means is two things can fail. Just like your car. Your car is an electromechanical device. So it can do what? It can fail electrically, or it can fail what? Mechanically. Okay. So these guys will wear out over time, and they'll have to be replaced. And a lot of times people will come in and they'll do stupid things. A lot of times they'll come in and pull the covers off the thing, and then what they'll do? They'll leave the covers off. As soon as they leave the covers off, and you're out there in the industry, you got all the screws that get into your screws, right? They'll put them on and they'll put them on wrong. And they'll get their operator, so the operator goes past its limit and break the operator off. So all kind of problems. But these guys are nice and rugged. They're very mechanically sound. So I did pass the limit switch around. Y'all need to see it again? Okay? Don't need to look at arcing contacts. We also, a lot of times, use what's nice about a relay is that your limit switch, we can buy smaller limit switches that can't run our load. So it's very seldom that we have a limit switch that can run a pretty good sized motor. But what we would do is we'd use a limit switch to bring in a relay, right, you understand, and then use the contacts of the relay to run the motor. Here what they're doing is they're saying, okay, I got a 20 amp load. My contacts are rated at 10 amp, and I'm trying to run a 20 amp load. Well, what would happen? It might run it for a little while, but it's not going to run it long, right? You understand? Eventually the contacts are going to burn out. But I could take that same relay, not even use a 10 amp relay, maybe use a 1 amp relay, a lot smaller relay. Limit switch. Bring in a controller, bring in a relay, and then let the relay run the water. Let the contacts of the relay run the load. Are you okay on that? So when we get into the programmable logic controllers, so what a PLC does, it allows us to replace every control relay and water control relays. These are devices where their contacts stay inside the control circuit. Timers. We're going to get into timers later on. Their contacts stay inside a control circuit. Counters. Their contacts will stay inside a control circuit. So all these devices that are totally inside the control section of a ladder diagram can be replaced with a program. But we still have to bring inputs in. We can't replace inputs, right? You understand? And we can't replace outputs. Sooner or later, that computer has got to send something to the outside world. So the PLC we could do all the decision inside the PLC to determine when a motor runs, but the PLC could not run a motor. But it can output enough current to bring in a relay that does what? Runs the motor. So PLCs have not done away with relays. What it's done is done away with the relays. It's done away with all the relays that don't require power contacts in the power section. But the inputs on those things are like, 20 milliamps. So you'll look at some of the limit switches we use on PLCs. They don't have to be nothing. But the PLC, we could bring it into the PLC, the PLC output could bring in a big contact, right? You understand? Most PLCs could run a 2 amp load, which would be a really good sized relay. So you want, like I said, program logic controllers are going to replace everything that stays in the watt circuit, in the control circuit. So it's going to be replaced by a program. But guess what you do? You use basically almost the same symbols that you're learning in this class right here, if y'all take PLC. So people ask me which one's the easiest to take. And what I tell them, you take PLCs first, it makes motor controls easier. If you take motor controls first, it makes what? It makes PLCs easier. We hear people say all the time, I wish I'd take motor controls first. And then we get the PLCs, I wish I'd take PLCs first. So these are some operators. So operators are the devices that actually make physical contact with the device. And then, of course, it's going to transfer that into the actual limit switch itself. We do have a rotary limit switch, which the operator has to create a rotational when it hits something, right? And then we have plunger, we have a plunger type, which they're calling the push type, where the actual operator pushes directly into the limit switch itself. And there's some limit switches that you can get where you put this top thing over here, you can make it either one. You can either make it a rotary limit switch or you can make it a plunger limit switch. That's very, very popular. You can look, this looks like it's what, to be what, removed. And then, of course, you're going to have some kind of slot. It usually comes in on the bottom. It's going to be a hole where you can bring your wires into the limit switch. The limit switch we have has the protection cover off of it. You can focus. Oh, here's a. Yeah, I gotta see that limit switch. I've only shown it to you. I'm talking about it. This is a name of motor control. Somebody took the overlay up there. Well, guys, I don't see it. Back on that back table. Oh, no, I'm sorry. Here we go. So y'all remember who I get these from. It's just that the one that I wanted to show y'all, the actual protection cover was off, that you have to take off the wire. So the one we have is in the roller type. This is the operator. Some of them are 2 positions, so this one's got a stop on it. So that means if I didn't mount this thing right and it came up here and hit that, and I mounted it wrong, you could break it, right?
Why the first push one you put fast around only had one?
Well, that's what I was saying. This is a lot of industrial and that's why I wanted to show you that. A lot of them gives you their design so you can just do stack them on there to get whatever you need. So you could put 2 normally closed and 1 normally open. You could put, and you can see when you, of course, the more you get on there, the harder it is to push, but yeah, the one I had only had 2. It's going to have at least 1 down there, right? It could have 2, or it could actually have more. And you'll see that a lot on industrial because that way the company don't have to keep a bunch of spare parts, right? So this is 2. This one only has 2 normally open. This one only has 2 normally closed. We buy what? A bunch of push buttons. They're all exactly the same, right? You understand? And then I do what? I build what I want, right? I build what I want. So this is normally, it has a screw in on it, and then it's got a strain relief clamp that you have to clamp in. And what it does is, and then it usually has a rubber flap on it that seals around that. And that's going to prevent anything from getting in here. So normally what we would do is we would feed our wires up through here, we'd take them through the clamp, and then we'd take off this top cover, and then it's going to have the connection in here. Here's the actual manufacturer numbers on here, where I have, this is a double pole single throw, right? You understand that? I got one normally closed and one normally open. Now the symbol, this is not the symbol, this is not the symbol of a limit switch, but it does show us normally open and a normally closed. So this is not a legal symbol, right? Everybody understand that? So what's the legal symbols? Now we're gonna start putting symbols on tests, because this is one of the things you gotta learn in this class, is learn the symbols, right? So what's the symbol for a limit switch? Normally open. So we start off with 2 dots, and we're gonna come over here. If it's normally open on these switches, we're gonna draw it down, right? And then we're gonna put something on there that indicates it's a limit switch. Huh? Yeah, a little ramp. It's more of an incline. Yeah, it's more of an incline. So we come up here and do that, right? And that would be a normally what? That's normally open. This would way it would be inside our diagram. Yeah, but it's going to be on the top. So normally closed goes across the top. Now, if it was drawn like this and it was up in the air, then it would be a normally closed held open. So these are symbols for our limit switches. Now what this would do, this would actually have a dashed line between them, if we could have it, on this guy right here, because we have a normally open and a normally closed inside this one thing, right? Okay. Limit switches should not be operated beyond the manufacturer's recommended travel specification. We just talked about that. So what could you do? What would you do if you operated beyond its travel specification? You're going to damage it, no doubt about it. You're either going to strip it out, right? You understand? Or you're going to break your operator, or you're going to bend everything up inside of it. But all these things are not equal. You need to make sure we have double way operate, so they actually operate all the way. This one only comes up to the center, right? So it only operates up to like 90 degrees, the one that we have in our, that we'll be looking up in our lab. Cam operated limit switch. This is kind of like what we have on our cycle time. So what a cycle timer does, it gives you in motor control, and we can simulate this. So everything that we're doing in this class, we can simulate a lot of stuff with in a PLC. It's going to be with a program. So that's the big difference. So what a PLC does, it limits a lot of hardware. Hardware in computers is you can do what? If you can touch it, it's hardware. And the more hardware that you reduce down and the amount of space it occupies, so we can put almost the whole control section of a pretty good sized program in a little box that's about that big. Now we're still going to have push buttons, and we're still going to have relays, right? You understand that? It's just like in your car. Do y'all have relays in your car? Where are they at? Usually, it's usually the box. Usually, you have a fuse box that's inside the passenger seat, right? And then you usually have a control box out there that has a bunch of fuses in it. But that's where all your relays. That's usually going to be under your hood. So cam operated, so you can see what they're talking about. So a cam means it might be a circle with notches cut into it. And, there's probably a cam operated limit switch. You've got an automated isolator in your house that determines when the temperature sensor says it's cold enough or it's frozen, then all it does is run a little motor. Most of you can actually hear and then it turns a cam, and then there's notches in the cam that tells it when to do what. Fill up the water, when to turn on the heat, right? You understand that. Puts a little heat on the bottom to loosen up the ice. Trying to find out what cam operated limit switch we have called. So what they're saying is that this cam operate, this is okay, this is bad. What are that? This might not be bad if it only turned in one direction, but most cams don't want the operator to snap and open and snap and open, so they want it to come in gradually, right? So most of these cams you'll see will have a slope to it. And what that does is that limits the wear and tear on the actual operator. So instead of the operator coming over here and doing what? Hitting a cliff and falling off, then normally what it does is we put a plateau on there so the operator can come up and roll up this thing, and when it goes the other way, it will do what? Go down. This guy right here, as long as we're turning in, not this direction, that's bad. If it's turning in this direction, it would just do what? It would just cycle. But if something happened and it went in the back direction, then it would break your limit switch, right? You understand that? So they're saying what we need to do. We don't want the operator to make really real fast, high speed, abrupt changes. We want to make it gradually change. Limit switches uses push rollers, actuators must not be operated by on their travel. Of course, we already know that. And like I said, you're going to see these things all over. Up the top, that's either a milling machine or a drill press. It's got an automated table on it, right? And of course, what they would have limit switches on each side. So normally what happens on these big milling machines is the mill don't, y'all know what a milling machine is. What's the milling machine? What's the difference between a drill and a milling machine?
The milling machine is they like it shapes stuff.
Yeah, it shapes. It basically cuts grooves and makes shapes. It don't drill holes. Drill machines don't drill holes all the way through something. So a drill would drill a hole, right? You understand? A milling machine might come in and cut a groove, or a milling machine might come off and smooth around the side, might go around the side of an object and clean it out. It might cut grooves into an object. So if you ever dealt with a router saw is a lot like what a milling machine does. So a router is not designed to cut holes, right? It's designed to do what? Cut shapes into saw. So normally on these big ones, the table moves, and the big drill press or the big milling machine stays stationary. And what they want to do is they want to know exactly when these things hit their ready. We had a planer. A planer, y'all know what, anybody just does woodwork and go with a planer? What does a planer do? A planer allows you to shave precise depths off of a piece of wood. And so you can make it really, really smooth, really, really pretty, or you can change the depth. If you've got a non-standard size, you can plane it off, right? You understand? So we had a planer out there that would plane metal plates, steel plates. And it had these big old planing blades that would drop down, and the bed must have been so they'd put the big plate onto the planer. And then what would happen is it had a bunch of planing heads down here, and the whole bed would move back, and then when it went this way, the planing blades would come up, and then when it went that way, the planing blades draw down. And that table was probably as long as this classroom, and probably about half as wide. We used to ride that thing all the time, but it had limit switches, so it would know what. So when it hit one side, it would know to do what? Automatically reverse it, and it would know when to raise the planing blade. And that thing was huge. And it would cut off. This was steel, guys, these steel plates. And what it was doing was setting precise depths on plates that U.S. Steel didn't roll. But they might have got an order for one, right? And their rolls would only do certain things. They had certain standard sizes that they made. And if they had a special order, that needed a real smooth surface or needed a smaller size, and they would put it on this big plane. And it was amazing. I saw some stuff out there that amazed me. Limit switches use push rollers or actuators or operators. I don't like to call them actuators, but operators must not be operated from their travel limits. This usually happens when you replace one, right? You either replace it with the wrong kind, or you come in there and you mount it wrong. You get it up too high, or you get it down too low. Limit switches should not be mounted. Limit switches should not be mounted. Avoid accidental activation, accumulation of material, and excess heat. So here they're showing us correct and incorrect. So the top one says that's correct. The bottom one says that's incorrect. And you'll see what we're talking about. What page is in the book? If you need a better picture. Huh? So what's wrong with the incorrect? Yeah, there's no shield on the limit switch that prevents what? Accidental activation. And so the one on the left, they did that. What's wrong with the next two? Do that often. Okay, that's one way to do it. So what's wrong with the one on the left? What's wrong with this one? The way they got it mounted. Yeah, well, all the debris falls right down on the limit switch, right? So all they did was mount it over and then put a cam at it. So here they was actually depending on the part that's moving. Here they mounted the limit switch on what's moving and they put the stationary cam at it, right? And then of course the next one should be obvious. What's wrong with the one on the right? Right above the fire, yeah. So what they did is they moved it to the top. We had a lot of doors out there, a lot of furnaces out there just that they could raise the doors on. And, they had limit switches on like this. They'd have put them like this on some of the fires out there that melt steel. Most of the furnaces, we had the Q-Bop made steel. The blast furnace makes iron. And then they bring that and they mix that with limes and carbons to make steel. So steel is harder than lime. Then they'll take the steel and then they'll let it set. And then usually they'll reheat it or slabs. And they get it hot enough to make it, put it in the plastic state. And then what do they do with that? Then they form it, right? Then they roll it while it's in the plastic state. The pipe mill, they actually roll it into a big round circle, and then they have a rod they stick down the center, so that's why it's called seamless pipe. So instead of taking a plate and rolling it over and welding it, like a lot of steel pipes are made, they actually jam a rod down to the center of that, and they put a clamp away around it to keep it from doing what? Expanding. So what does it do? Well, it extends. So it's real strange. They'll have one that might be 20 feet long, and they'll drive that ram down to there, and it ends up being 60 feet long. So they'll put a clamp around it so it can't spread out. Pretty neat. Even though I never worked over there. A foot switch is used to allow hand-free control of an additional control point. So we see these. A lot of press machines have foot switches on. Anybody work at a place that's got these foot switches?
I used to switch to TIG weld.
Yeah. So that way you gotta have both hands free, right? So TIG weld, a lot of TIG welders have a foot switch on it. Also, sewing machines have foot switches on. We used to have a foot switch in our cars. That's the way we dimmed the headlights. Anybody remember that? You probably still got it. It's on the left-hand side. You hit dim or put the bright lights on dim or bright. Now it's up on the control. So this is a symbol for a foot switch. Everybody okay on that? This is a single pole double throw with the center off. Normally we don't put the motor starter way out here. It does that on the book. Normally we try to put our relay contacts over on this side, right? But this guy does this often where he'll stick that out. This is a reversing controller. We got two relays. One of them is going to run the motor in what they consider to be a forward direction. One's going to run it in the reverse direction. And then notice we do what we call electrical interlocks. Notice, let's see what I'm talking about. So what happens if something happens and the forward and reverse happen to come in at the same time, then we would create a short circuit. Because the way you have to switch the wires on the motor. So to reverse a motor, you got to switch wires. So I could rewire it to run always in forward, I could rewire it to run always in reverse, or I could bring those wires out and then I can control when the motor goes into reverse or forward. But the problem, we do that with either a switch or something. Later on we'll do it with relays. We'll look at a forward reverse control circuit with relays. And I don't know if we got one wired up. We got one on the PLC. What we want to make sure is that these two relays can ever come in at the same time. So can you see what it does? So notice this runs it in forward, but this guy's got it. This runs it in reverse, but there's a normally closed forward contact, and this one runs it in reverse. This runs it in reverse, but there's a normally closed forward contact. This runs it in forward, but there's a normally closed reverse contact. So what happens if I put this up this direction, it'll come up and run it in forward, and it'll open this contact, so there's no way in the world what the reverse is going to be able to come in. And we call these electrical interlocks. And you'll see that a lot on reversing controls, just to prevent the forward and reverse relays from ever can come in at the same time. Every reversing circuit I've ever seen, if you let those two relays come in at the same time, you have a short circuit. Are you okay? Questions? Okay, guys, y'all take a minute break. So this is what we're getting to, what we refer to as non-contact sensors. So these are sensors that do not have to make physical contact with what they're trying to measure. What they do in motor controls represent an electronic switch, which means these have an electronic circuit. So this down here at the bottom is no way here the way this thing should be laid out. And so basically what we have is we have a sensor, which odds are it could be what we call a photodiode. Now the photodiode, notice it's got arrows pointing in, so this guy here detects light. And then what we're going to do is we're going to run this into an electronic circuit. Now the problem with electronics is electronics does not work without power, right? You understand? So our power is going to be between L1 and it's going to be between L2. So these guys are going to have to be powered up. So notice we have one wire coming from L1, and then we have another wire that runs over to what? L2. Now in motor controls, as soon as you see that square, that diamond shape, this means this is, most people call it's electronics, but most people call them solid state sensors. Now these are electronic, but what does solid state mean? It means there is no moving parts. Everything is done electronically. So we don't have a physical contact in this thing. We got an electronic circuit device that acts like a contact, right? that we can turn it wide open, turn it wide on, or turn it off. Then we got a control output that comes off. So this is where our load's going to be at, whatever it is. Normally it's going to be a relay. These guys are not designed to run a lot of current. They can provide enough current to bring in a relay, and a relay can run your load, right? You understand? So here they're going to turn on a light. So notice, here's the diamond. As soon as I see this, I know this is what? Solid state electron, which means it's going to have to be powered up somehow, right? You understand that? Then what they do is they just draw a switch assembly in here. And then sometimes they'll put the light in, sometimes they don't. Sometimes you have to look that up. So what happens, this powers up the electronics. And then, of course, when this thing senses light, then it's going to electronically simulate a closed switch. There is not a closed switch in there, it simulates them. These things are not going to click. And then what's that going to do? That's going to make the rest of the run become true. So most of these guys, we got some we'll talk about a little bit. They're going to have at least 3 wires coming out of them, right? And the color is standardized, guys. So here's a 3-wire sensor. This is a photo sensor. Okay. And let me blow it up. Oh, so can y'all see the colors?
Red, black, and red.
No, it's brown. Brown, black, and blue. So what would be the signal wire? You would think, no, it's black. Yeah, it is. And that's what gives us problems over here, because we think of black over here. Most of the time we use black for common. Over in Europe, they don't use black for common. They use brown for common. And then blue is hot or plus, yeah. And then the black would be the signal wire. This is a 3-wire sensor, so this is going to simulate a normally open switch. But there's no moving parts. So when this guy sees light of a certain intensity, then what it's going to do? It's going to simulate closing a contact. And then when it don't see enough light, it opens the contact. But there is no physical contact. We have these guys all over the place. Some examples.
Traffic signal light.
The traffic signal light wouldn't use this guy.
They have sensors.
Well, no, what would happen, the sensors on that, those are not photo sensors. So those things are on 24 hours a day, 7 days a week. Some people call these dusk to dawn switches. So when it gets a certain darkness, they activate their load. When it gets certain light, they deactivate it.
Like city street lights.
Straight, yeah, just about all used to before they came up with these things. Street lights were on timers. So what would happen is that, you'd go around in the summertime and the street lights would be on, right? Because they had set them to come on for winter. So what you had to do is you had to do what all the time? You had to retime them for the season. Now they don't do that because they use dawn to dusk sensors. We call them, technically, most people call them photo cells. We have them on our street lights, all these lights out here in the parking lot. We have them, motion detectors at my house. They don't turn my lights on during the day. They only turn them on what? If it senses motion at night. So very simple, but there's non-contact. You don't have to see anything. All it's doing is seeing light. And we can vary this on what we do. We can use them to count. So I could put a light sensor on one side and a light on the other side, and anytime something passes through it and breaks the beam, we could use them to count, right? You understand that? Or we could put the transmitter in here and the receiver in here. We can shoot a light beam out and then let it reflect off something and bounce back in. So these light detectors, we have several different categories we'll look at that we need to understand. Oh yeah, that's what they do. They usually trigger stuff. Most of these guys, we can use them for what we call proximity. So when we talk about proximity sensors, these are going to be your solid state sensors. Limit switches, even though they sense proximity, they have their own name. So we have limit switches, and then so now when we use the term proximity sensor, we're talking about a solid state sensor. And what that means, and these are what we call non-contact sensors. So a limit switch is a contact sensor, which means what? It's got to make physical contact. That operator has got to hit something out there to do anything. So it's got to make physical contact with what it's going to measure. These are solid state. These are not electronic and mechanical devices. These are electronic devices, which means what? There's one less thing that can fail, right? So why do we still have limit switches? Well, they've done their job for a long time, and they're a lot cheaper than these solid state sensors. So you're still going to run into limit switches all over. But you're also going to run into places where you don't want it to make physical contact with anything. So Mercedes has got a $50,000 car down there that they just put a fresh coat of paint with, and they want to sense when it's at a certain position. They're not going to use a limit switch. They're going to use some type of non-contact sensor, right? It might be what we call a through the beam. But what we do know is if I see this diamond shape, it means it is a solid state sensor. Right? You understand? If I don't see the diamond shape, then I'll have another, and the problem is solid state sensors basically have usually have about the same symbol. And you just normally you have to figure out what they are. Oops. So this is a photo. This is a photo. We don't call them light sensors. We call them photo sensors. So technically they call photo sensors, right? You understand? And then we got several categories. So we could come up here and so where's our light sensor at? And what I want to do is insert and we'll get in, if you take the sensor class, we'll get into more detail on these things. So we have one where we can put the transmitter on one side, and then we can put the receiver on another side. And then what we do is we shoot a light beam across. And then if the object comes through here, so these guys would be true all the time, right? That makes sense? Their outputs would be true. And then when the object comes through and breaks the beam, then it would know the object's at a certain place. That's what we call this guy. We call it through the beam. So here you're going to have a transmitter and receiver. So when we go over there and look at the manufacturing line, we'll show y'all through the beam sensors, we'll show y'all diffuse sensors, we'll show y'all these different sensors. And then we have one where the transmitter and receiver is in the same unit. And then what it does is it shoots a beam out. And then when it hits the object, it uses reflected light. This is what we call a diffuse sensor. So we'll show you all those over there. These have limited range, and also we have a problem with color, right? You understand? So different colors reflect a different amount of light. So if this right here was a black object, what might be the problem? It might not reflect enough light for it to come back, right? Okay. So we call it diffuse sensors. Through the beams, and another problem is the limited range, because the light that travels out has to come back. So through the beam has the ability to have the longest range, because the light's only going in one direction, right? You know what I'm saying? And then the last one we have is what we call a retroreflective. where we have a transmitter, and then we have a receiver, and then we have a reflector right here. So the transmitter shoots the beam out, it hits the reflector and does what? Bounce back. And what happens is the object that we're trying to sense moves between the transmitter and the reflector. So it works similar to the what? Through the beam, but this only has one unit. The transmitter and receivers in one unit. And this is a retroreflector. A retroreflector is an object. It could be a triangle. The street department uses little beads. So I don't know if you ever seen them paint things that reflects back, but they'll come up here and put paint down. They'll throw all these little crystal beads out there. And what those are retroreflectors. So a circle does basically what a triangle would do, which means it will return light back to where it came from, as long as you're within what we call a viewable area. So this is why when you're looking at a stop sign, you can see that the stop actually glows, right? Because it's got a retroreflector on it. And people that ride bicycles wear retroreflective vests, because if it was a mirror and you were here and your light struck it like that, it would bounce off like that instead of doing what? Bouncing back at you. So that's what a retroreflector is. A retroreflector is a reflector that returns it back to the source even though it's not aligned. So there's a retroreflector up on the moon. So NASA will shoot a laser beam up there every once in a while. And so it don't have to be aligned perfect, right? You understand? And time how long it takes to get back. So they know the speed of the beam, right? You understand? So they can actually measure the precise distance to the moon. Used to, it was guesstimated. Now they know exactly how far the moon is. And they know it's what? It's moving away. Something like, what, 2 millimeters a year? It's actually drifting out. So when your grandchildren's 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 grandchildren might not have a moon, that's when we're really going to have climate change. So here's the three basic types of light sensors. They're all going to be 3-wire sensors. Why do they need 3 wires? One is going to be the signal wire and the power wire coming from what? From L1, and then you got to make a direct connection to L2. So that right there. So these solid state sensors, most of them are going to have to be powered up, right? We do have what they call a solid state limit switch that powers up through the load. So it draws very little current. It does drop a voltage, but it don't drop enough to affect the operation of the circuit. Any questions here? So I'll show y'all a retroreflector. Y'all seen these things before. This is pressure. Of course, we need pressure. What do we need pressure for? Normally, we need pressure to generate force, to make things move. So forces are what cause things to move, right? Y'all know the formula for force? Anybody had fluid power? Hydraulics, pneumatic? Yeah, times pressure. So how much force you generate is how much area that pressure is pushing against, right? So this is why you can put 34 pounds in your tire and it can hold up. You say, well, that's only 34 pounds. How does it hold up a 5,000 pound car? It's spread out across those tires, right? It's pushing against the wall, a lot of area, right? And then it's divided between 4 tires. So we have so sensing pressure would tell us how much force we're going to be able to generate. It becomes important when you're using impact tools, moving robots around and stuff like that, or grippers, different tools that we found on our robot. So maintaining a good pressure really means something. So we have pressure sensors. We have pressure gauges, we have pressure sensors. What a pressure sensor will do, and like I said, we'll show you all those on the manufacturing line. It's going to indicate if it's above a certain pressure or below a certain pressure. And a lot of them have an adjustment on it, so you can do you can set where it goes between a true and a false. And we'll show you all that. So we have all different types of sensors. We got an electronic pressure sensor back there. This is a diaphragm pressure. This is the sensing element. Now, a lot of sensing elements you have to combine with another sensing device to come up with a sensor. So this is called a diaphragm type. So what happens? What we want to measure, what we want to set the pressure or detect the pressure to, is mounted against this sleeve right here, and then when it pushes, it would cause this rod to extend, right? And then what we would do is we would come out here and maybe mount a limit switch out here. So when it got up to a certain pressure, it would do what? Break the switch. So a lot of your sensing elements on your pressure sensors and some of your temperature sensors, we have to combine that with another sensor to come up with what it does. So this is diaphragm. Let's see what else I got in here. And this is what we call a Bourdon tube. Can y'all see it's around here? Bourdon, B-O-U-R-D-O-N. So notice in the shape of a D and it's hollow. So when I put pressure in here, then what's it going to cause the C to do? Yeah. Anybody remember the party board? Yeah, that was a Bourdon tube. So it's in a circle, right? And then what do? When you blow on it, what did it do? It wanted to do what? Yeah, open up. And that's all a Bourdon tube is. Yeah, this Bourdon tube is made out of metal. Are y'all saying something the rest of the class needs to hear? We okay? So this is hard to see because it doesn't have a good color. But this is the input. This is the Bourdon tube, and then it moves. And then we would have to mount a switch on this, right? You understand, to sense when it got up to a certain pressure. This used what we call a mercury switch. So there was a tube in here full of mercury, and then when it got up to a certain level, the thing would swap sides. And when it did, it would close the mercury switch. Now, we don't see many mercury switches anymore. Why? Well, we can. We just got to be real careful with it. Mercury is what they call carcinogenic. The guy that causes brain problems. But its molecules are so thin. Its molecules are so small that they'll go right through your skin. So it's real dangerous to handle mercury. And the problem with mercury is a metal that has a melting temperature probably, I don't know, maybe below zero. So basically the only time we see mercury is in its molten state. I've never seen mercury in a solid state, but it is a metal. It's just got extremely low melting temperature. But it's a pretty good conductor. So what they would do is they would mount contacts on each side, or one side, and they'd have two contacts, and when the thing flopped over, the mercury would come up and cover them up and do what? Close the contact. And these were very popular in old thermostats. If you get into an old house and it's got a dial thermostat on it, it might have a mercury switch on it. Huh? Well, water is an insulator. Unless you put a bunch of impurities in. So distilled water is a really good insulator. So water in itself is not a good conductor. But it's what makes water conductive is the garbage we put in the water, right? You understand? So sweat's got a lot of salt in it. Salt has a low resistance to electrical flow. When you put that in water, we worked at a place where they made big old generators, and they wanted to check the current output on them, and they didn't have a resistor that would work. So they got a big old plastic vat, and they put distilled water. They filled it up with water, and then they'd put the two outputs of the generator on there, and they'd start pouring salt in, and they could change the resistance that way. And they had to get pretty high because eventually I square R, the water would start boiling. But they used that to do what? And then they had an ammeter on that thing, and they was looking at the output of the generator at the number out to see if the thing regulated correct. But they actually used water, but not water. They used what? Salt water. They used salt water, and they buried the contents of the salt water. So we couldn't use water. We can use, most metals are really good conductors of electricity. And so mercury is a good conductor of electricity. It's just that it's hard to use because it's always a liquid. But they would put it inside a glass tube. That was the problem. They put it in a glass tube because they couldn't put it in a metal tube because glass is a good insulator. And what would happen is people would break that glass. My dad used to bring mercury home, and we used to play with it when I was a kid. We played with it until my mother came in there, and someone was on the floor, and she touched that mercury with her gold wedding band, and and it wicked all into her ring and turned her ring silver. And she was mad. So my dad didn't bring mercury home anymore.
It ate the gold?
No, it turned it silver. It wicked onto it. It plated it. So mercury to gold is just like a magnet. So as soon as that mercury got close to that gold and it hit it, it just did what? Just wicked around that thing, and then it turned the wedding band silver, and I can't remember what she did about it. I just remember being mad.
You know?
I don't know I think she got it clean somehow. Somehow she took it someplace and they was able to get off of it, but we couldn't before she was. Here's a bellows. We have different things. Piston types. Just a diaphragm. I was looking for a bellows. I think I got a bellows. Here's a limit switch that's opened up so you can actually see. This looks like it's got a bird pack. This has a different type of operator. It's almost like Santa Claus, right? What else? This is an old thermostat. And y'all might still have these in your house, guys, if you get into a real old house. Well, be careful around these things. And that's a mercury switch right there. So this is a bimetallic strip. It's in a spring. And so when it heated, it would cool down. It would go into a tighter circle and cause us to tilt, or it would go this way. So this way, that would be an open circuit. And I don't know if you can see the wires coming in back here. So this is my contacts. So when the bimetallic strip got to a certain temperature, then the mercury would fall over and cover those two contacts and would turn on my heat. On my floor furnace. I don't know what gas floor furnaces do. Now we got HVAC systems. Everybody had gas floor furnaces when I was a kid. So these were furnaces in your house that ran off natural gas. And this is what turned them on and turned them off. But this is glass, guys. I'm not going to pass this around because y'all could do what? Yeah, break it. And then we have mercury all over the place.
That's the green machinery?
What's that?
The mercury stuff?
No, it's silver. It's real pretty silver. Really? Well, it's because of the camera. The camera's not getting enough light, so it's got a yellow tint to it. So if I was to actually put a light on this, so on my picture, It looks nice and green, nice and silver. So that's what was originally mounted in this little tray right here with the mercury switch.
How's mercury bad for the brain?
Huh?
How's it bad for the brain?
Yeah, say that for me, Maurice. It causes brain cells to die. Right, and mercury, and that's one of the things they test for. And like I said, it used to be all over the place. We used to use it in burglar alarms for cars. That when they would jack your car up, when your alarm, it would go off. Now they use a metal weight that flops around in there. But this used to, so if you got a real low burglar alarm on your car, that you engage your burglar alarm when you park. It used to have a mercury switch on there, so if somebody jacked up your car to try to steal your tires, it would set off your alarm. So this was another sensor. We'd have to combine this with something else. This is called a bellows. And so what would happen is we put pressure on this side and it would cause the bellows to do what? Expand. And then we could set like a limit switch or something up here. When it hit it, it would indicate we hit a certain pressure. It would drop down below that. And we do have solid state stuff. So this is the bellows. Whose turn is it? We do have solid state pressure switches, but on our diagram it would all use the same symbol, right? You understand? This is a solid state. This came off a compressor. So this has two switches in it. So it turns off at 100 psi and cuts back on at a 70 psi. So we have a deadband, or we call it a hysteresis, that we can set. So this is a pretty standard for a home compressor. So your tools are run at what? Most of if you ever look at your tools, standard tools, they run at 60 psi. You're supposed to run at 60 psi. A lot of people run them with more. Yeah, but you're going to cause them to go bad faster, right? Because the seals and everything. Yeah, my wife's, my son's wife's brother was using a nailer from Harbor Freight. Guess what? It blew up in his hand. He was in the hospital for a while. That's scary. Huh? A nail gun. It was a framing nailer, so it was a big nailer. It was a framing nailer. You know, hardly nobody uses hammers anymore. They buy these nail guns. I still got a hammer. So this is what we just showed, is what we call the deadband. So a lot of times, especially on a compressor, they'll have one switch that closes when it drops down to a certain level, and then they'll have another switch that closes when it gets up to a certain level. What happens is it cycles between those two levels, right? So this allows us to use what we call, so if your compressor is running all the time, guys, it means you need a bigger compressor. Most of the motors that run are what we call, they're not continuous duty motors. They're what we call intermittent duty motors, because they're designed to cut on and cut off and cut on and cut off. So if you got a compressor that the motor runs all the time, then odds are you need a bigger compressor, right? Or eventually you're going to burn your motor up. So that's what I just showed y'all. Did I pass that around? No, I didn't. So this is a pretty straightforward switch. So what's the symbol for a pressure switch? No matter how it senses the pressure, or how it takes a pressure and converts it over to electrical signal, it's going to use the same symbol. And what's the symbol for a pressure switch? So we have a normally open pressure switch, right? And we come down, and then we put a half circle. So half circle for a pressure switch, right? And then a normally closed, of course, we would come above, and then it still has the half circle. So this is a symbol for a pressure switch. Here it is right here. And these, all I passed around, these are not solid state, so they don't mean they have to be, they don't require external power to operate, right? Pressure switches are used to maintain predetermined pressures in a tank, reservoir, or sequence of the term. We measure, weather people measure atmospheric pressure, so they have pressure sensor that measures at our tank. They measure it in bars, right? So we have pressure sensors in fluid power systems. We have pressure sensors in heating systems, boiling systems. We have pressure sensors on almost anything that's going to run off pressure. Any questions? Yay, nay? A low pressure switch may be used with metal. It was amazing to me. Have you ever seen these water jet cutters? That's amazing. That they can cut metal with water. Low range pressure switches can be used with a metal tubing arrangement and a pneumatic sensor to determine what is a sensor? What is a sensor? Y'all should know this. Y'all have had my classes before. So my brain has no idea what smell is. My brain has no idea what sight is. My brain don't understand what hearing is. My brain don't know that. We sense things through what we call sensors. So what does our body sensors do? What does our brain process? What does our brain process? What do we send it? We don't send it touch, sound. My brain has no idea what touch and sound is. We send it electrical signals. So what our sensors does, it converts a physical stimulus PHP. I know I got physical. I got my INS reversed. Stimulus into a what? Electrical signal. All ours are what we call digital sensors, which means our electrical signal is either going to be off or it's going to be on. Most of your sensors are analog sensors, like your sense of touch. We can hard, soft, we can do all kinds of stuff. So what you get from your sensors, you get an electrical equivalent of, and then it comes into the section of your brain that processes touch, and it says, okay, I've got this big of an electrical signal. That means you're touching this thing this hard, right? You understand? In your eyes, you got 3 different sensors, right? What are the 3 sensors we call them? No, I'm sorry, we got 4. We got cones and rods. I think the rods detect shades of gray, and then your cones detect, we have a red, blue, and green cones in our eyes. And then that comes into our sight, and your brain combines all that, and it don't see, it sees the electrical equivalent and translates that into what? Into sight, into what we see, which is amazing. So our sensors are doing the same thing. They're going to take a physical quantity like pressure, like light, like sound, like heat, and convert it over to an electrical signal so we can process it with devices that use electricity. So like relays. Relays work off electricity, right? You understand? So I can have a sensor, and digital sensors mean that they're either going to give us they're either going to let the signal pass through, or they're going to do what? They're going to block it. It's not going to give us an equivalent voltage of what it's actually. So I don't know the pressure. All I know, the pressure has exceeded a certain value. I don't know the light. All I know is the light has exceeded a certain value. And then if it exceeded the value that's either built in or adjustable. So a lot of your digital solid state sensors are adjustable, which means they got a little knob on them, so you can say this. Now, if you look at the pressure sensor for that compressor, it's set for 70 psi on the low side and 100 psi on the high side, and you could not adjust that. The pressure sensor that we'll use in sensors, we have the ability to set the low side and the high side. We have the ability to set the threshold on that sensor. Are we okay? So a sensor, it does what? Converts a physical stimulus into a what? Electrical signal. And that's exactly what your senses do. How many senses do we have? I got about 50 senses in my body. Yeah, we say we have 5, but actually we got a lot. That's just the 5 they teach you. We got a lot of senses. We sense balance, right? So we don't talk about our eardrums sensing what? Balance. We can sense heat. Sensing heat and sensing touch are 2 different things. So you have different nerves that sense what? That sense heat, then senses cold. So we can sense balance. So there's a lot of other senses that we have. We know what's up and we know what's down. So we know orientation. So we have sensors that keep us what? Oriented. So in a heating system, heat is produced when the temperature switch contacts closed. So temperature switch. So this is the symbol of a digital temperature switch. These are not solid state. If it was solid state, it would be inside of what? A diamond, right? Everybody okay? So where are we going to run into temperature sensors at? I got one in my house. I got a thermostat on my wall, right? Where I can do what? I can adjust when my air conditioner cuts on or cuts off, or I can adjust when my heat cuts on or cuts off. And those are done by temperature. I got a electric oven in my house. Yeah, you can that's an analog sensor, right? We actually measure the analog on it. But I got a light, I got electric eye. And the problem with electricity, it takes a little while to cool things off. So it turns red, right? After we cooked on that, and it's telling people, even though the eye is off, don't touch the top because you're going to get your butt burned, right? Yeah, you got a temperature switch in your car that tells you when it's over temp, right? Even if you got an analog gauge, most cars have an analog gauge on it that tells you a temperature, but then it's got a light that comes on that says what? Over temp, yeah. So you're going to run into monitor temperature is pretty important. Temperature sensor, you got electronic temperature sensors. When you've got a fever, you stick one in your mouth or under your arm or somewhere else, right? When you're a baby. So they're going to give us some examples of temperature sensors, but these guys are going to be all over. Anytime that temperature could affect the operation or is required. So your oven temperature sensor is really accurate, and it's analog, right? So I can come now and set my oven to 225 degrees, and it'll come up and do what? You have 225 degrees, cut itself off. If it drops below that, it'll do what? Turn back on. Cooling systems, temperature sensor switches. So if you got a gas heater, I guarantee you there's a temperature sensor on the firebox that will let you know if it's a lot hotter than it's supposed to get, right? Iron's got a temperature sensor on it. So you set it for cotton, and what does the iron do? Comes up, and sometimes it's got a relay. Sometimes some of your bigger irons, you guys hear the relay clicking off the temperature sensor. So HVAC systems got temperature sensors in them. You know, like I said, compressors have temperature sensors. Some compressors, boilers have temperature sensors in them. So these are different types of temperature sensors. Let's go ahead and take another 10-minute break, guys. First one they show up on the left, it's called a bimetallic strip. And the way these things work is they take two dissimilar metals, or two metals. They can't be dissimilar because if they did, they would interact with each other. And then they would bond them together, and the two metals would have different y'all know metals, when we heat them up, they expand, and when we cool them off, they contract. Well, what they do with the bimetallic strip is they bond two metals together that have different coefficients of expansion. So what happens is when we put a current through them, or when they sense temperature, they'll warp. So they'll bend. So the one that's got the highest coefficient of expansion, which means it expands more, it would cause the strip to come up and warp. Now, if we put that thing in a circle like this, if you cool it down, it would have a tendency to close the circle down, right? A coil in. If you heat it up, it would tend to uncoil. And this is what they're showing you here. So that's what I showed you a while ago. Here they're using a mercury switch. And then, of course, when this heats up, what does it do? It wants to uncoil and would cause the mercury switch to tilt and close the switch. But we could put, so this one looks like it's set up for cold, right? Because the mercury switch is on this side. And so if it cools down, the thing's going to come into a tighter coil, and it's going to cause this to do what? No, it's heat, because heat would cause it to go this way, and cold would cause it to go that way. And heat would cause the mercury to do what? And then tilt to the left and cover those two contacts and close that switch. And then what you had is you had an adjustment on the thing where you could set the tension on it. So this is the way you actually set the temperature on your house. So this is actually the same thing we're just looking at. So over here is where you'd set the temperature. So over here would be your temperature gauge, and this would show you. And when you turn it, can you see what it's doing? So what you're doing is you're setting how far the strip has got to do what? Coil up before it actually makes the switch out. And this is where you would calibrate it at. So you'd come up here and you'd move this around. The person that set it up or built it, they would use this to calibrate it. So they'd put it up against a known temperature, and they'd set this until the switch, and then they'd set this at the same temperature and calibrate it so the bulb would move. And of course, like I said, we don't see many of these anymore. Well, that's not true. You'll see them in older installations. The industry has a tendency, if they've got something that's going to work, they're not going to replace it with just something new to be new. Right? It's just like me. When I go out and buy something new, normally it's because I can't get parts for my device anymore. So people joke at me about so when I replace a washing machine, it can't be fixed anymore. Y'all understand? So that's what we're saying. So you'll see a lot of that in the industry. So if you get into an industry that's been around for a long time, what are you going to do? You're going to have a lot of old stuff, and you're going to have a lot of new stuff. As long as their old stuff is working, they're going to do what? Keep it working. Gerald's Milk. I don't know if you've ever seen Gerald's Milk. They package Gerald's milk right off of, you can see it in the grocery store. It's powder milk. They package that right off of 4th Avenue down there, down where the old, where they do the pipes stuff down there. I don't know if y'all know where I'm at. Off the bus. Yeah, I think it is. They got a church over there too. But I was in there when they converted over from an old, totally mechanical system to a totally electronic system. And I was helping them to convert it. And, the way that old one did it was amazing. But they kept that thing around. So if the electronic one ever failed, they would do what? They'd fire up that old one again, and, so they could stay in business. Another thing we have is we'll use a bellows tube. They had one of these sensors out there, so it had a hot glue gun. It had a hot glue, so they put they packaged the milk in a package. They seal it up and then they put it in a box. And then of course they glue the box together, right? The actual gluer, they wanted to keep it at a certain temperature. So what they did, instead of putting a temperature sensor in there, they put a capillary tube in there. And the capillary tube ran up to the bellows. And what happens to air when it heats up? Expands. All that thing had was just air in it. Or it might have had a gas, but anyway. And when it expanded, it would cause the bellows to do what? To spread out. And then they would trip, when the glue got up to a certain temperature, it would turn off the heat. So that sucker had exactly that thing. Then we got our solid state sensors. We have what we call thermistors. These are semiconductor devices that sense temperature. And then we have what we call thermocouples. Thermocouples, the way a thermocouple works is that it works off of what we call dissimilar metals. So when we combine dissimilar metals and we force them together, they'll literally they'll create a difference of electrical potential. And what that difference of electrical potential is proportional to the heat. So what's nice about a thermocouple is that it actually creates a voltage that is proportional to the temperature. And then the type of thermocouple we have would depend on the temperature range. So if you're going to measure temperature and you wanted to do it fairly precisely, then the thermocouple would be the route to go. So your oven, if you've got an oven in your house, it uses a thermocouple. Or if you've got something that needs to control something when something's at a certain temperature. So if you've got a gas water heater, you notice there's no electrical wires going to the water heater. There's none at all. But it knows when to turn on the gas and turn off the gas, right? Well, the way it does that is it does it with two things. It does it with a thermostat, and it also does it with a thermocouple. So there's a thermocouple. So gas water heaters has a pilot light on it, right? And then it's got a thermocouple that comes up and does what? Sets in the pilot light. Now what that thermocouple is doing is telling it's allowing the main gas valve to open. So that way if the thermocouple is not good, or if the pilot light's not lit, it won't turn on the gas. Just because your thermostat up here, which is electrical, right? It's powered in your house. So it controls the valve, but the thermocouple prevents the electrical pulse, the electrical signal off the thermocouple prevents the main valve from opening if there's not a pilot light. So that's a thermocouple. So thermocouples, we use these. What's nice about thermocouples is they don't have to be electrically excited. They create a voltage that's proportional. The problem we have with a thermistor is that it's nonlinear. So notice a thermocouple, it varies its voltage, and look at the straight line. So anything that varies in a straight line, we say that's linear. A thermocouple is not a linear output. So notice it does not vary in a straight line. Its resistance changes. So a thermistor, let me get this right, it varies its resistance with temperature. But its resistance it varies is not linear. Y'all understand that? So I'm not going to use a thermistor for an accurate measurement unless we combine it with some electronics that compensates for the curve. Now, normally, we'll use these things if we can use them over a very limited range, then they appear to be linear. So if I use it across that range right there, it's a pretty straight slope, right? You understand? So normally thermocouples, if we're going to use them, we use them over a narrow range. Or we're going to use it to switch at a certain temperature. And then that way you just adjust your electronics till it switches at that temperature, right? So we use thermocouples in our house. So this is my old digital thermostat that I took off my house. Now, what's nice about your house is you maintain your temperature between a very narrow range, right? What ranges do y'all use to keep your house at? So what's the coldest you let it get? Yeah, 60 and 72. So that's only a 12 degree range. So since we're using it on a very limited range, the thermocouples work out really well, and they're pretty cheap too. So this is my old digital thermostat. So this is the first digital thermostat I got when I moved away from one of those. Okay. And then of course this is the thermocouple. This is the thermistor right here. The little thing that's got the little white dot. Huh?
The white?
Yeah, it's white and blue. So it's got a little white dot on top of it. And then it's got springs wrapped around there to compensate for temperature inside the sensor itself. So thermistors are used in digital sensors a lot because you're not trying to measure a temperature. What you're doing is you're going to trip it off when it gets up to a temperature, right? You understand? Or you're going to trip it on when it gets down to a temperature. So thermocouples are fairly expensive, but what's nice about thermocouples is they're really accurate, right? They're linear, and of course they generate a voltage that's proportional to temperature. And you have different metals that will give you a different temperature range. So I don't know what's used inside your a lot of your I don't think I got one. We call them digital multimeters. Now, to be considered a digital multimeter, you got to measure at least 2 quantities, right? But normally ours measures at least 3. And what's the 3 that we are most concerned with? Ohms, amps, and volts, right? Okay. But that would be like a car coming. So used to, but then we started adding stuff to make them more sellable. So most of your digital multimeters now measures more than what? Volts, currents, and ohms. And what's some of the things? So temperature is very, very popular. And what they'll do is they'll provide a thermocouple. And they'll look and they'll have, if you ever look at the very tip, you can see where they got the 2 pieces of metal do what? They're actually bonded together. I thought I used to have one in here, but I think it was used. I think I hit the bottom of my bag. So what you do is you have your meter, you have it on the temperature scale. You flip it on temperature, but you still plug it into the same inputs that you use to measure voltage. So all you're doing is measuring a voltage, but now your meter is doing what? Translating into a temperature. So what's the problem with thermistors? So what advantages does a thermocouple have over a thermistor? It's got 2. It generates a voltage that's proportional and it's linear, right? Which means it's going to give you, if I knew this thing gave me 10 volts for 100 degrees, if it gave me 5 volts, I know it'd be 50 degrees. If it gave me 25 volts, I know it was 25 degrees. So its voltage is going to be what? I've said it wrong because I started with 10. If it gave me 2.5 volts, I would know it would be 25 degrees, right? You understand? So it gives me a voltage that is proportional to temperature. What a thermistor does is it varies its resistance. So a thermocouple can be used by itself, a thermistor can't. So a thermistor, we're going to have to power it up. We're going to have to power it up. Normally what we do is to power it up, we have to put at least two resistors. Because if I came over here and put one thermocouple, one thermistor, the voltage would be constant. Now normally what we sense is we sense the amount of voltage, right? Because voltage we can measure across. Current we have to measure to flow through. So just about all your sensors are going to give you a voltage, right? Does that make sense? So how would I get a voltage out of from a thermocouple? From a thermistor indicating a temperature? If I came over and did this. So if that was 12 volts, what would it always measure? It would always measure 12 volts, right? You understand? So what we normally have to do is we'll come over here and we'll put it in series with a fixed resistor. So now when the thermistor varies its resistance, this voltage right here would vary, right? Because we got a fixed resistor, and if it drops less voltage, that guy's there going to drop more. So normally we have to use these guys that vary their resistance, we have to put it in series with at least one resistor. And normally we put it with a Wheatstone bridge. Did y'all do Wheatstone bridges in DC? So if you take sensors, we'll get into Wheatstone bridges. What a Wheatstone bridge does, it allows us to establish what zero is. So a thermistor would give us a certain resistance at a certain temperature, but it would be, what we'd like to do is be able to set a zero reference, right? You understand? So what a Wheatstone bridge does is they should be able to set a zero reference. Calibrated, yeah. Well, not really calibrated, it's just set it from zero. So if I came over here and did this at some degrees, 32 degrees, or let's do centigrade. So 0 degrees, this guy right here might have 2.5 volts out. Well, I would like it to have what? I would like it to have 0 out, right? You understand? So now it means something. Well, a Wheatstone bridge, which would take more, I couldn't do it with this arrangement. We would put it inside what we call a Wheatstone bridge. And this would allow us to set a 0. And so like I said, so what we would do is this would be my thermistor, and then this right here would be a rheostat. And what I could do is I would adjust this to it. So I would take my thermistor and put it into a glass of ice water, right? You understand? And then I'd adjust that resistor to my meter measure 0. The advantage of a Wheatstone bridge, it allows us to set a reference point for a sensor that varies its resistance. It allows us to set our reference point to a point, right? You understand? So y'all didn't do Wheatstone bridges in DC? When you was doing series parallel circuits, y'all didn't do Wheatstone bridges? Oh man, I'm gonna have to talk to our DC people.
That's probably 2016.
Well, you're still on it. Wheatstone bridge is one of those terms you might not remember how it worked, but you'd remember the what? Yeah, the term, yeah.
You took it last semester. I don't remember that.
Who taught you? I need to talk to you. Because this is really good for series parallel circuits, because it's not really a complicated circuit. This is the way this is the way they draw it, but it's actually just, it's this circuit right here. That's all a Wheatstone bridge is. But what we're doing is we're taking our voltage output right there. So if this is 1K, and this was 1K, and this is 1K, and this is 1K, and I had plus 10 volts across here, what would my meter measure? So I know these are the same size, so I know they would have to drop the same voltage, right? You understand? I know the total voltage drop would have to equal to 10 volts. since they're the same size in a series circuit, we know, right, the current is the same. So that's one thing in a series circuit. If you got two resistors in a series circuit and you calculate one drops 5 volts and it's a 1K, and over here you got another 5 volts, another 1K, you might as well write 5 volts on there, right? You understand that? So I know this guy here is going to drop 5 volts. So that means reference to common, I would have plus 5 volts there. Reference to common, I'd have plus 5 volts there. So what would my meter measure? Got plus 5 volts on this side. I got plus 5 volts on that side. What would my meter measure? So what's the difference in potential between plus 5 and plus 5? What's the difference in potential between plus 5 and plus 5?
Plus 5 and plus 5.
Yeah, what's the difference in potential between plus 5 and plus 5? Now, if this was plus 3 over here and that was plus 5, everybody would come over and say, well, that's a difference in 2 volts. But here I got plus 5 on that side and plus 5 on that side. What would that meter be? It can measure 0. And we call this a balanced situation. So a bridge is balanced when the ratio 1 on this side matches the ratio on that side. So what we're saying, if this was my thermistor and it had 2K at 0, then I can come over and adjust this right here to 2K, right? And then the voltage here, this would be balanced. This might be plus 7 volts now, and this might be plus 7 volts now, but it'll measure 0. So what I can do is I can adjust this to get a 0 reading, right? You understand? And then now, when this guy here rises, this voltage would go up, and we would have current flow through the center. I had an argument with the guy that was teaching DC when I was taking it. I said, well, when the Wheatstone bridge is balanced, he had a resistor in the center. I said, when it's balanced, you can pull the resistor out and it would mean nothing. And he said, no, you're changing the current. And I said, but Clarence, there's no current flow through it. So I went and got my OX buddy, Mr. Walters. He was the department head at the time, and he came over there and straightened out the teacher. So like I said, you know, if you have 7 volts on both sides, there's no current flow through that center thing, and don't mean anything. So that's why. So normally when we use sensors that vary their resistance, and we need to set a 0 reference, we'll set it up in what we do things we call a Wheatstone bridge. And that way it gives me the ability to do what? Set 0. So what I would do is I would take this sensor, I would put it in a glass of ice water, and I would adjust this till my meter measures 0. And then if the temperature went down, my meter would measure minus. If my temperature went up, my meter would measure plus, because now the bridge becomes unbalanced. So it's a pretty important concept to understand in instruments. So we used to teach Wheatstone bridges when we got into series parallel circuits. The problem is y'all don't spend much time in series parallel circuits, do you? Huh? Yeah, but this is a pretty simple circuit to understand. I mean, flow switches. We don't have any flow switches. Everybody understand flow switches? Flow switches are usually just vanes we put down inside the flow. It's just like when you're kids and you're driving along, everybody's done this, roll the windows down to do what? Put your arm out. What do they call your arm to do? That's basically what flow switch does. They just put a vane down inside the flow. They seal it up real good, put a spring on it. Water fluid comes through, pushes against the vane, makes the outside move, and they flip the switch when it gets up to a certain. Now we have flow sensors. That's hard to get a sense of flow, but we have different type of flow sensors that we can do that. But a vane is probably one of the most popular used on a flow switch. So what's the symbol for a temperature switch? It's not a hook switch. What's the temperature switch? Huh? Yeah, so this would be a normally open. We drop down and do what? Yeah, go this way and do what? Go that way, right? Some people come over that way too. That would be normally open, and then this would be normally closed, right? So what's the symbol for flow switch? So y'all know what's going to be on the next test, right? Yeah, so the flow switch basically has a little flag out on it. Yeah.
Which, upside down flag.
Huh?
That's the way to remember that. It's an upside down flag.
Yeah, that's what it is. And the flag does what? It flops in the wind. So this is the flow switch. I think maybe they were. I know the bimetallic. I know the temperature switch was. Normally closed, normally open, flow. This is the one that's very, very popular. Just a vane. We call this a vane type. And what does it do? Just pushes it up, right, when it flows through there. We're getting into more complicated. So how would this circuit right here work, guys? Oh, they missed line 2. Oh. Line 2 should be right here because it's supposed to line up with the line, right? So what would this do? Push start button, should seal itself in, right? It's got an M. I know that's a magnetic motor starter. How do I know it's a magnetic motor starter? I got overload. Good. Motor starts. Wind starts blowing. Yeah, if it don't get any flow, then it's going to do what? It's going to sound the alarm, right? Everybody okay? Pretty easy. Yes, no? We don't have any flow switches, so we can't. So how would this one work? This is using a magnetic motor. By the way, this right here, we haven't got here yet, but this is they're calling them TRs. These are timers. This is a symbol for a timer contact. So this contact is being controlled by this guy. Now, this is what we call an on delay timer. So if the arrow points toward the switch, it's an on delay timer. If the arrow points away from the switch, it's an off delay timer. So what do I mean by an on delay timer? So what happens is that this guy right here, on delay, I come over here and this flow switch is closed. I have M1, we have flow, it's going to start energizing the timer. Let's say the timer is set for 5 seconds. But what happens on an on delay timer, it starts timing when the rung is true. So that means this guy, when this guy is energized, this contact does not close until what? 5 seconds. And then the contact will close. An off delay timer, I got off delay. Y'all probably running an off delay timer like in your car all the time. I mean, I got, so when I open my doors, my headlights come on. When I close my doors, they stay on for a while. A little while. That would be an off delay, right? I used to, on your dome lights, they used to go off instantly on older cars, but now when you open your doors, they'll come on and when you close them, they do what? They stay on a little while, right? So those are examples of off delay timers. The washing machines use on delay timers. So they'll come in and you start it up, and after a while they'll turn on water, right? You understand? And then after a while they'll do what? Do that. So those are all on delay timers. So this was an on delay timer. So an off delay timer, the symbol would be, and we're going to teach timers later on, the different types. But an off delay timer would look like this. So an off delay timer, the arrow points what? Away from the switch. An on delay timer, the arrow points toward the switch. So here's a pretty cut. So how would this work? So we got a 3-wire control, memory control, it's also called the ceiling circuit, right? I know this is a motor starter, I know this is not, right? But then it's a relay, so if it's a relay, it's gonna have contacts. So these are what?
That's in your car.
And what do they show us? They show us the line that the contacts are in. These are what?
Those are line numbers.
Line numbers, right? So I come in here, I press the start button. That's gonna come up here, it's gonna close this, right? It's gonna come over here, it's gonna close this, right? You understand? So what's this guy gonna do?
Start time.
It's gonna start timing. So what it's doing is it's giving time for flow to occur, right? Y'all understand? So we know that flow doesn't occur instantly. So it depends on where your sensor is at, right? So if the flow doesn't occur after 5 seconds, then it's going to come on and turn on something else, maybe another blower motor or something like that. If this guy here, if flow does occur, then what's going to happen? If it occurs before 5 seconds, then that's going to de-energize the timer and it's going to reset. So these are what we call non-retentive timers, which means what? If you de-energize them, if they're up to 4 seconds and you de-energize them, the next time you do it, it's going to start over. Right? Everybody understand that? So what else do we have in this chapter? Smoke detectors, I don't know why they got in here. Smoke detectors is a switch that detects the set amount of smoke caused by smoldering and burning material. Activates a set of contacts, which usually does what? Yeah, you ever heard one of them go off? Your mama's in there cooking something? Cooking something that generates a lot of smoke. Which most houses now have a ventilator hoods on top of it. What's this? Yeah, but these are flow switches. So this is what we call a 2-level control. So we have an upper level switch and we have a lower level switch, right? So what should the upper level switch do? There's going to have to be some control circuits in this guy. This won't go directly to the pump. There's going to have to be something in here that does what? Yeah, there's going to have to be some type of control in here. So what would happen is the upper level should, if it's below this one, the pump should come on. This is not going to do anything, right? Understand? And it's going to fill up until it does what? It's that one. And then it's going to sit there, right? How long? Until the pump drains it out. And when it drops down to here, it should do what? Start eating. So there's going to have to be some logic to that. Alarm sounds if overflow this. So they got a float switch up here. So that's what we hadn't talked about, float switch. So float switches. So they got a float switch. So what's a float switch? So these are 2 float switches right here. We do have float switches. So this one would mount this way. I'm sorry. And then it's got a tube here. This is the actual, well, we're not going to talk about how this works, but what happens is when it gets up and does this, right, it's going to trip it. Here's another type of float switch, which is...
And that's the way the one in your bathroom working?
The one in your bathroom is, yeah, like this. But it's a float switch that's controlling a valve, but it would be doing the same thing, except it's controlling the flow of water. And so what it does, it sits there, and if it falls down, it opens the valve, right, you understand? And then when it gets up to a certain thing, it closes the valve off. Yeah, so that's a float switch, but instead of controlling electricity, then it's controlling water. But if I can do that with water, then we can come up with some way to do the same feature to do what? Control electricity. So these are only 2-wire devices. These are not solid state devices. Now, is this normally open or normally closed? I don't know. I think it matters on which way you mount it. So I think what you would do, you'd mount it one way, and then it would be a normally closed. You mount it the other way, it would be a normally open. I think that's the way it works. Now this guy, this one, here's the float right here. So as the material builds up or the liquid builds up, this would cause it to rise up, right, and close the switch. And then this right here would cause it to open. Now this one, you change it from a normally open to a normally closed, and we're not going to explain why, by snapping this off and reversing the float. So if you reverse the float, one way would be a normally open. You snap this off and turn the float around, it turns it into a normally closed. And like I said, in sensors, we would explain how that works. We don't really need to know that. All we know is float switches are either going to be normally closed or normally open. Now, what do we use float switches for? Well, float switches only work with liquid. Where's an example of float switch? Most of us now, we have a light that comes on in our car that tells us when what. It says it don't tell you you're out, it tells you to do what? You're low. Now, the Harley Davidson motorcycle has we call it a dead man switch. Anybody ride a motorcycle where you switch it between the reserve and you don't actually have two tanks. What you got is you got a wall in there that it fills up, and then when it drops down and gets on the second one, you're supposed to switch it when it starts sputtering on you, which means what are you supposed to do? Yeah, so you're leaned over in a curve and try to get between your legs. And then what do you forget to do? You forget to change the valve back, you fill your tank up, and then you run out of gas, right? Because you don't get the sputter. Has that ever happened to you? I had a Honda Shadow, and it had this nice red light on it that would do what? It'd come on telling me you need to stop and get gas. I love that. The Harley, I ran out of gas once. Once was enough. So float switches check the level of senses when it's at a certain level because it's a switch, right? It don't sense the level. So what we're doing is we're dealing with digital sensors, which means they're going to tell us when something gets up to a certain value, right? So a digital temperature sense would tell us when we got up to a certain temperature or we got below a certain temperature. So a float switch tells us when we either get up to a certain level or liquid gets up to a certain level or get below a certain level. So in your car now, you got a float switch back there. You've got an analog switch, right, that tells you the amount, but then it's combined with a float switch that does what? Comes on and says, you know, you need to stop and do what? Hit gas. So what's the symbol for a float switch, guys? Right? So this has a full bubble, right? Oops, that's supposed to touch. Could be called a level switch, yeah. That's what they call it here? Probably a liquid level switch. We have conductive probes that depend on the conductance of a liquid to sense its level. So these would not work with like still water or something, but anything that's got any impurities in it that we can put a current through, we could sense that. Or not a current through. We have what we call capacitive sensors, which the current does not flow through them, but we can control the amount of current flowing through in and out. So the fuel level sensors that we had on our airplanes were capacitive. It was just two tubes, one mounted inside the other, which formed the capacitor, and when the jet fuel got up in it, it would give us an indication. So the one that we have is just a basic, just a float switch. So basically, a liquid level switch would be a type of float switch, right? So I don't know if we're going to go any further in this chapter. So capacitive level sensors, optical level sensors, distance sensors, which we won't run to a lot in motor controls. And combining sensors, so we can combine sensors to get more complex tasks. By the way, one of the things we're going to run into is, and for some reason, and this is going to be in your lab, is when they set up a timing chart for ands and ors. So they'll come up here and they say for an and. That has nothing to do with this chapter, but it's in the previous chapter, and I know this is in your lab book, and I want to give y'all a heads up so y'all can figure these things out. So let's say we do an and I think we might have done one of these in class. And then on the next break, guys, we're going to be back over in the mechatronics lab. We can actually look at some of these sensors. Y'all know where that lab's at, right?
Yeah. We all did.
Where my office is at?
Yeah.
Wrong. Not that way, James.
Yeah.
That way.
All the robots.
This building is real easy to get turned around in because you come up those staircases that wrap you around. So, believe me. My office used to be in this building, down in A250. I'm trying to find the third floor. So the way the timing drives are set up, so this would be what type of logic? Yeah. And what they do is they call this like A and B, and then we have a relay over here. And then what they'll do is they'll come over here and they'll start these things like this. So they'd say this is going on with A, and then they'll say this is going on with B. And then what you're supposed to be, so this would be A, this would be B, and you're supposed to figure out which one represents. You don't have to draw C, but they're going to give you 3 or 4 different answers, and you got to pick out which one's right. So this is my output. So what would my output look like if this right here was true and this down here was false? Well, my output would come over here, and this says all these have to be closed, right? Yeah, so we'd get this right here, and then it would drop back down, right? And then I'd come over here and over here and over here, and then it'd go right there, right? And then it would stay where? Right there. And then I'd come over here, and then it would go up like this, and then it would go down there. Now what they're going to do is they're going to have 3 or 4 different answers where you got to pick out which one would be for a true and, which one would be for an or, which one would be for a not, right? Y'all understand?
Because you just have a horizon.
Well, what we're trying to do is, this indicates when the relay is energized. So this indicates the contacts are closed. So every time one of these contacts are closed, it's going to let this guy go over to here, right? You understand? Okay. So what these are what this indicates is when the contact is closed. And what this is energized, this indicates that the relay is energized. So on an AND, all the inputs have to be true, right, for the output to be true. Okay. So what we're saying right here, A is closed, but B is not closed. So the output won't be what? Yeah, so if I come over here and look right here, at this section right here, okay, so right here, they're both right here, right? But if I come over here, let me change colors. Now A is true, so A is closed, but what? B's not, right? So here it's still what? Understand, Bernard? So what does an AND say? Well, that's digital. A and B have to be closed before my relay is energized. So when is A and B closed? So is A and B closed right here? A is closed, but B is not closed. So the output is not energized. Here, A is closed, B is closed, so the output would be energized. Here, A is closed, but B is not closed, so the output would not be energized. Right? Here, A is closed, but here A is not closed, but B is closed, so the output would not be energized. So what we have to do is the output is only going to be energized at that time. Now, I didn't get this lined up exactly, guys. So if I was to come over here and identify all these edges right here, so this one should line up right there. And this should have lined up right there. So when is the output energized? So I forgot this one right here. So the only time the output is energized is when both A and B, so here A and B is closed, so the relay would be energized. Here A is closed, but B is not closed, so the output would not be energized. Here is A is not closed, B is not closed, so the output would not be energized. So the only time the output is energized is when what? When they're both closed. Now if this was an OR, let's change it back. Let's say, okay, now this is an OR. So let's, what we would do is let's just erase the bottom. And how would I do an OR? You know, we put our contacts in parallel. Now B's down here. So what would happen here? So this is an OR. So here I would do what? So let's identify the edges again. I'll do a little better job. I know I'm slanting, guys, but it's good enough for schoolwork, right? Okay, so this says an OR. So what would my output do? So, yeah, so we'd start off what? This would be, let me do a different color. Are they doing exercises outside? So this would be what? Start off true, right? And here it do what? Go false. Then over here it do go what? Back true. And then it would stay true all the way over here. Then it would go false. And over here it would go true. And then it would stay true all the way over here, and then it would go false. So that would be the same two signals, but for what? An OR. Y'all understand? Huh? Y'all see where this is in? This is on one of y'all's chapter quizzes. I don't remember which one, but I saw it in there the other day. Huh?
It was on our lab.
No, it's one of the it's either on chapter quiz. I think it's in one of the chapter quizzes. What's that?
Yeah, it's a question like that in our lab.
LD 39.
LD 39. So what we do to start our next class is we'll go through the labs that we have the capability to do now, right? You understand that? I think Bernard and Roselle's a little ahead of the class. They've wired up a circuit that we haven't gone over in class. So what we like to do is actually go over the circuits in class before y'all wire them up. So what we're going to do now is we're going to go over y'all can take a 10-minute break. And then meet me over in the mechatronics lab. Don't go in, the mechatronics lab is the lab right next to the robotics lab. Because they got a classing section inside H107. So it's the room next door, right? Park in the lower lot instead of coming in the door that's got, beside all the glass, come into the next one that's by the stairwell.